Yeah, most of the stuff they got wrong was over circuit theory, which I'm always terrible with circuit theory.
All right, some feedback on the midterm exam. The first one, I don't think I see major issues on that, which means 80% of the guys got 100% for the first problem. A Thevenin's equivalent will give you a circuit like this, and only one R here, and then the cap. So it's a very simple RC circuit. So time delay is going to be 0.7 RC. Okay, we have done this for 3 times at least. This guy, you can see I removed a little power supply here to confuse you, and you did get confused. It's just a resistor network, right? I mean, I don't know why you guys are not making this right. So if you see this one, you treat this one as a output network, right? Okay? And the whole thing here is a load, right? Whole thing here is a load. So superposition. First, you short this guy to ground, and you can convert this part at the Thevenin's equivalent, because you can see the 2 resistors. It's just dividing the voltage by 2 halves, and if you look backwards, it's a 1K resistor as well. So eventually, this part becomes this, right? With the output network, it's 1K, and with the 2.5 volts. Okay? It's actually easier than the situation when you had a extra one here, but now it's gone. So I was hoping that this can save you a little bit of time during the exam. And you short this guy, and connected here, you got 2 resistors. It's a 2K resistor, so overall you have a 3K. And then you got a voltage divider, right? And because this is shorted to ground, it's 2K. And this is the output. So we got a V1, which is the voltage divider, 2.5 volts times 2K divided by 5K. It's 1 volt, right? It's 1 volt. Okay? And when this is shorted, only this one is applied to the circuit. It's shorted, so it's got 1K, 3K. So it's a very simple voltage divider circuit. 2K, 3K, V2 is 5 volts times 3K over 5K, which is 3 volts. So V out is V1 plus V2, which is 4 volts. Any questions on this?
So you just combine the first 2 resistors in parallel, right, to get that 2.5 volts? And then
This guy or this guy?
the first one.
This one?
2.5 volts.
Yeah. You mean this part?
Yeah.
Yeah, it's a Thevenin's equivalent, right? So when you just look at this part, this is the output node, right?
Yeah.
And you're looking backwards from here, right? It's 2 branches and go to ground.
Yeah.
So it's 2 parallel, 2K in parallel, it's gonna be 1K, right? So that's RTH.
And then you just multiply the V7 is Vn times R2 over R1 plus R2, right? So then V1/2 times 5 volts, right? Which is how you got the 2.5 volts.
It's a VTH. VTH is you calculate. So VTH is when you remove the load from the output network, right? So the voltage appears here will be VTH. And you can see this is the voltage divider, 2Ks, 2.5 volts for VTH.
Okay.
Just 2 steps. You have to follow these 2 steps. Got VTH, got RTH, right? It's 2 steps.
Yeah.
And then you find these 2 values, and then you put it back to the circuit, connect the load to it. So the load give you a 2K here and 1K here, 2K here. Okay, and so voltage divider got 1 volts and 3 volts when you look backwards. Any questions on this? No? This one, 80% of you guys made it right, and so the only major issue is that we place the poly on the top first, then we deposit P plus materials. So the poly will block that P plus material from getting diffused into the substrate. So that's how you form a channel. You don't want to directly draw a universal P plus over there and have a with the poly on the top. It won't happen that way. This is how you form a transistor in the channel in the middle. So this part is blocked because you place the poly there first. It's blocking. So when you deposit the P plus material, it's blocking that from deposit into the substrate. So you're getting a channel, right? So it's P plus, P plus. That's the only major issue I found. This one, this is from Google, this picture, and this was wrong. I told you guys during the study session a week before, and this needs to be put up to VDD. Okay, so when here's a 0, right? So 0. When you connect this one here, what is the signal here? If the switch is being placed on the top, what's the signal? What's the voltage here? 0. It's being shorted to 0. Right? It's 0, right? 0. What is here? It should be 1. Okay, it should be 1. So if this is 1, this is 0. You are setting or resetting it. Remember, it's RS. Setting or resetting. You are setting it, right? So this is the 1. So once this one is flying in the middle, take a slow motion, flying in the middle, and there will be a bounce. It's bouncing from 0 to 1, 1 to 0, whatever. It's a memory because whenever it's switched to 1, it's a memory. So 0 is still setting, right? So it's not changing it because the non-gate version of the debound circuit, if you put a 1, 1 here, is a memory. Keep in mind, it's really easy to understand it and memorize it. Not really. I'm not trying to let you guys memorize it, but the thing is, it's trying to leverage the benefit of using ones. Whenever they are both ones, it becomes a memory because the non-gate version of the SR latch takes ones as a memory state. Why? Because why is this easy to remember? Because 1 is not. You put a 1 here, is not changing whatever the result is. The result only depends on the other side of the input. The 1 is not changing this guy. The 1 and anything else is still that thing, right? It's not changing it. It just understand this one. You can always figure out what's going on here. If the non-gate version, you need the both ones, right? Because whenever it's flying in the middle, it's bouncing back and forth. It's the ones. You need the both ones as a memory. So for the NOR gate, I'm also asking you guys to use the correct symbols. That's the NOR gate symbol, right? Don't have another thing here. That's the XOR gate. So it's a NOR gate like this, and this one you need a pull down resistor. You need a pull down resistor for the NOR gate version. Why? Because 0 zeros are memory inputs. Oh, sorry. So 0 zeros are memory inputs for it. And for this pin, you have a VDD here, and that's a switch. Okay. Q nut. If this one, because this is being put down all the time, if there's no switch being connected to it, so this was 0, right? And you want to pull this down to 0 as well. So whenever this is bouncing back and forth, it's going back and forth from 0 to 1. Whenever it goes to 0, it's not changing the state. It's a memory. For this one, I had a lecture on it. I didn't even change any of the simulations since I was so lazy. But still failed like 50% of you guys. It's exactly the same problem from the class, right? Okay. If you don't know how to solve it, watch the lecture, record the lecture. I have a video recorded about this. For this one, I added little 1 here. So for Q3, I'm only looking at Q3 but nothing else, right? So the Q3, it's gonna be A naught, B naught, and this guy, which is AB. Okay? If you are an experienced electrical engineer, you can figure out this is NOR logic. No, it's a, what's that called? XNOR. It's XNOR logic. And XNOR is what? XOR not. Okay? You need to know that. So this is what? A not B or A B not. This should be a 2 second thing during the exam. You can save a lot of time. Right? From this to this. If you know this to this, it will be very simple. And now I got a bar on the top. Looks really enjoyable. So I'll start doing my AOI logic schematic. You have to have a bar on the top. So then you have AB, which is A not B. That's gonna be this, right? A not B. And AB not. So it's given that only A and B are inputs, so you need the inverters if you need a B not, A not, B not. Okay. So but now let's we can add it. Always we can add it later. So let's do this for now. A not B, 2 in parallel, and 2 in parallel. And 2 in series, 2 in series. So A not B, because there's the order here, so we want to do A not B. I want to align it. This is AB. This is A not B. And A not B, AB not. And this will be AB not. Inverter, easy part. You need 2 inverters, right? 2 inverters. Okay, so put an A here. So I got an A naught. You put a B here. This will be B naught. Okay. And if you have different colors of markers, you can make certain connections. But I think this will be good enough. If you show the inverter, show the Z diagram, and show this one correctly and logic, I'll give you full credit on that. If some of you didn't really align them, I also gave you the credit. Didn't take points off, but in the final exams, you make sure that you align them exactly, because this is not a super difficult one to align, right? So you can definitely align them. So which means all the A's are A's, B's to B's, so reduce any tangle wires. Any questions on this? Are good? Okay. Now let's talk about charge pumps. Before we do charge pumps, we're going to look at the circuit of voltage doublers, rectifiers. These are the basic circuit blocks for this concept. Why do we want to talk about charge pumps? Because it's being used for the sample and hold circuit for the ADC. Okay, and there's a chapter on charge pumps in the textbook. You can find out and you can read it through. The examples from the lecture notes will be the examples mostly from the textbook. So let's start with a voltage doubler first. What's a doubler? Here's a voltage. Oh, I don't want to ground it. Sorry. And if I draw this, two terminals, and two terminals here. And you're probing at these two terminals. So you have a switch. You can either short it this way. So first, if you put the voltage, if it's V, like voltage V, yeah. If you do this, what's going to happen? At the moment, you have a switch, but always in the integrated circuits, you can see a lot of modules or models using switches, but the switches are eventually becoming transistors, right, to control it on and off. But we model it using switches. If at the moment we switch it on, these two on to these 2 points, and you can see
it charges the top.
yeah. So what's the voltage here?
It's
V. Okay. If we switch it down here, what's going to happen? It charges here, right? So, but before, so when we switch it down here, are the charges here being lost or not?
No,
it stores there, right? It stores there because there's no way to discharge it. It's all disconnected. There's no way to discharge it. It will store there. So someone is gonna do this. Okay. So after that 2 events, what's the voltage at the output? It's gonna be like 2 batteries, anode to cathode, right? What's the voltage of it? 2V, right? 2V. So you got the voltage doubled. See? It's doubled. Just a very similar concept. Very similar concept. Okay, so the model here looks like this. Just show you the concept. Plus minus B, and you're getting 2V here, right? So that's the model of it. And if you look at the voltage doubler, we have to start with the basic circuit of the rectifier, like this. If I run a sine wave, the output is going to look like what? Just a resistor here. So input, it's a sine wave, right? Input is sine wave. That's V in.
Well, it'd be
For V out.
It'd be half, right? 'Cause it would,
So when it goes up, it goes through the diode, right?
yeah.
So it's able to go through the resistor and creating a drop.
See.
So the voltage here is going to be the same as this guy, right?
Yeah.
So you are getting the same voltage here. But whenever it reaches 0 and start getting negative, what's going to happen is the voltage here will be higher than voltage here. So it's trying to push current backwards. But is it able to push current backwards?
No.
So what that means there's no current.
Yeah.
Okay? There's no current.
Which means there's
No current means what?
no voltage.
No voltage drop. So it means these two voltages will be the same. If I'm measuring the output as the voltage differences between the two nodes, and what the voltage would be during that cycle, whenever it's negative. 0 volts, right? It will be this. Okay? If I add a capacitor at the output, okay? If I add a capacitor at the output, we all know that if we don't have a capacitor, it looks like this. Bumps. The capacitor, what's going to happen and why?
Like slowly decrease and
Slowly decrease why? It's discharging through the resistor. It's like charging up the cap, and whenever it's going to 0 volts, right? When there's nothing can go through, and this one starts discharging through the resistor. So it's gonna charge up, and discharging to a certain point. Okay? To a certain point, and then we'll go back up
Yeah.
whenever you got a cycle going up again, right?
This, yeah.
So you're gonna do this.
And that reduces the AC component, right? It makes it more AC signal.
Yeah, it looks like a more DC, but you have a lot of ripples, right? Depending on the resistor capacitor values you are choosing, you can have a big capacitor to maintain the charges more steady, more stable, and then you have less ripples, less changes over here. But this is a half wave. This is called a half wave. Rectifier, right? It's being used for transformers. So you got transformer output. Use a half wave rectifier. It can convert the AC signal into DC, right? And then do a regulator after it to stabilize it to your digital voltage level, like 5 volts or something, right? If you have a full wave rectifier, we're not going to cover that. It's the analog stuff. So the full wave rectifier will be able to reduce this even further because the full wave rectifier is giving you continuous bumps like this. So you have less low voltages, and eventually it's able to reduce the amplitude of the ripple a little bit to make it more stable, right? So that's a full wave rectifier output. So the voltage doubler is very similar to this circuit, but you only need to swap the location of the capacitor and the diode over here. So it looks like this eventually. What's this? Yeah, that's a voltage doubler.
No resistor.
No. I see why this works. For example, input, right? I got digital voltage, 0.5 volts at the beginning. What's going to happen? 0.5 volts as an input. So which is here's 0.5 volts higher than here, right? So negative 0.5 volts because the bottom is higher than the top. If I label this plus minus like this, okay? So negative 0.5 volts means this is 0.5 volts higher. And let's ignore the built-in voltage of the diode, so which means it's able to charge up the cap that way. Okay, so it's going to charge it up. So what's the what's the voltage across the cap after this cycle?
0.5.
0.5. Where is plus? Where is minus?
Plus is on the left. Minus is on the
No, it's
Oh, wait, no.
charging up.
It's on the right. Sorry.
Okay, because negative voltage, right? So it's actually doing this,
Yeah. So
doing this.
Yeah, it's on the right.
Okay. What do we observe here? If you probe it, if I ground this point, what's the voltage at VL?
The negative 0.5.
Where's ground?
We're just
0 volts, right?
yeah.
What's the voltage here from here to here?
From
From here to here is what?
but
No,
that's
from here to here.
That's 0.5.
So what's VL?
That means, well, it'd be negative 0.5 because
Mm-mm. Hmm?
would it be 0.5?
So
It's one.
no, no, you don't have many options, but none of the answers are right.
Confused. Because wouldn't it have to be the same as the capacitor?
Is it 0? It's not 0.5.
So you start from the reference. So when I'm talking about what's the voltage here is comparing to where?
Comparing to ground.
Compared to ground, right? So yeah, I'm probing. If I have a multimeter, the black probe is over here, the red probe is over here. I'm probing these two nodes, right? Differences between these two nodes, right?
Yeah.
So you only need to tell what's the difference between these two nodes. That's it. You guys are seniors.
Difference between these two.
So where's 0 volts? Here, right? So 0 volts, I already labeled it. So from here to here is it decreased by how much?
0.5 or negative.
Decreased by 0.5 volts. So what's the voltage here compared to ground?
So that's negative 0.
Negative 0.5 volts, right? And from here to here is being boosted by how much?
Well, if you're going left to right, it'd be negative 0.5.
Yeah, it's being boosted by because it's minus plus, right?
Yeah.
So the voltage here is negative 0.5 volts is being boosted by 0.5 volts, and it's the first grade algebra. What is that?
0.
0. So the voltage here is going to be 0 volts. That makes sense? 0 volts here, right? So after the first cycle, if this voltage here stays at 0.5, negative 0.5 volts, and this charges up, and you're actually getting 0 volts in the next cycle, because this guy was charged up, and there's no place to leak it because this is the cathode. So it's trying to leak through. Boom, it's a wall, hit a wall, right? And there's no load, so there's nowhere to go. So this charge stays. It's a little bit confusing. That's why we need to bring this up because it's an important concept to understand. In the future, there will be a lot of circuits running the same way, and you need to have this kind of thing model built in your mind.
So this.
Okay, so this guy stays. It stays. First time you charge it up, and second time, and it becomes 0 volts.
So yes, if I'm understanding this correctly, V out is 0 because of the fact that voltage is negative, and so therefore the charge can't dissipate to ground through the diode. Because otherwise, wouldn't it be the voltage across the diode? Because it has to go through the diode to charge the capacitor.
It goes this way to charge up the cap. Yes,
Yeah.
it goes this way to charge up the cap.
Yeah.
Yeah, and it stays.
Okay. Yeah.
So if let's go to the next cycle. So if this one, let's see. If this one keeps going, right? Keeps going. Become 0.5 volts. Same circuit. What is VL? Input becomes 0.5 volts now.
Yeah. Which then,
Does this charge stay?
no, it starts dissipating.
No, it stays. There's nowhere to.
At the moment that it switches?
Yeah.
Is that what you're asking?
Yeah, I mean at the moment,
Yeah, so.
but it's not going anywhere. We can tell later. But now, at the moment, I switch it. So it was negative 0.5, right? At the moment here, I switch it to positive 0.5.
And it's
So that's why I have this one. So this was 0.5 volts at the moment. So what's VL? 1.
Oh, and I guess it's not. It can't dissipate because the diode's stopping.
Now we look at this. At the moment, it becomes 0.5 volts and it's become 1 volt. Is there a reason for this charge to dissipate, to discharge, or be discharged?
I guess, no, because the diode would stop needing for discharge.
Mm-hmm. It's the disconnected circuit. You got 1 volts overall, and here this point is positive, this is negative. So the higher potential here, lower potential here, right? It's trying to push current that way, but it cannot because it's hitting a wall here. So it stays. So now, if I have an input oscillating between negative 0.5 volts to 0.5 volts, I'm getting an output what? Oscillating from where to where? So what? A very simple question here right now. So it's just one cycle, okay? You're asking, hey, what about the next cycle? Is it changing for the next cycle? So if I have this one come back, the input comes back to negative 0.5 volts, am I changing? So what's the voltage here becomes? The output.
0, right?
Yeah, it becomes 0 again because it's just got flipped, right? It's getting 0 again. It's going back to 0. And then after that, I do this. It becomes 1. So it's going to oscillate. So the output, the input, is this. And the output becomes 0 to 1.
How is it a square wave?
It doesn't matter. What do you mean? How is a square wave?
Is there any reason why it's a square?
Why is a square wave?
Yeah.
Yeah, because the input is a square wave.
Oh, okay.
Yeah. You could apply a sine wave. It's gonna work the same way. I mean, for voltage doublers, voltage. Oh, did you learn that in sine wave in analog?
No.
But that's a very good question, though. I mean, so did you cover this in analog?
We're doing diodes.
You're doing diodes right now. Okay.
Yeah, we covered it.
You covered voltage doublers, voltage multipliers.
No, well, we
No.
didn't cover voltage doublers, but we did do full wave rectifiers.
Okay. But you know the thing is, if you simply swap these two devices, and you are forming a voltage doubler instead of rectifier. So the voltage doubler is doubling it because the amplitude was 0.5 volts, but now it's 1 volt. Right. So you are actually doubling that amplitude. Okay. And after that, you add a cap at the output. So we know here is oscillating from 0 to 1, right? And if you add the output, add the capacitor to the output, it's very similar to like a low-pass filter, right? Low-pass filter. So what's going to happen is it was doing this, but if you add a capacitor at the output, it's trying to add a time delay to it, and eventually, if you have a big enough capacitor, it will not be able to discharge efficiently. So it's going to do this for the output over here. Okay, and you are forming a DC voltage at the output. DC 1 volt, very close to 1 volt DC. And you can use this 1 volt as a baseline and keep adding circuits out next to it, and you can form a voltage multiplier instead of voltage doubler. So if you add more stages after this, and you can keep boosting this voltage to like hundreds of volts. Mm-hmm. That's a lot of. It's a commercial circuit actually. So a lot of high voltage generators are using voltage multipliers. So they just pick up the correct diodes and capacitors and adding like 10 stages, and eventually can boost it to like 2,000 volts or something. Okay, that's how that works. But it's a digital circuit, so we are not dealing with that. So.
Is this how they convert pulse width modulation into like an actual voltage, like going from that pulse to an actual straight voltage value?
No.
Okay.
But similar. That's a very good question. So the thing is, the pulse width modulation, when you connect, right, connect this to a LED, you can say, because this is pretty fast, like you even a lot of times in kilohertz frequency, and you couldn't even see this getting blinked, right? You couldn't see it. Or sometimes I just know, you can probe this output to see what that looks like. But the thing is, this one could be because there's a built-in, it's a junction capacitor inside, so this becomes a low pass filter, and eventually the output will do this as well. Okay, that's one part. Another part is it's being blinked. So if you consider the output power in general compared to the DC power, like 5 volts, if you do a PWM, depending on the duty cycle, you can reduce the overall power being delivered to the LED by different DC levels. It's equivalent power being delivered to the LED, so you are seeing this being dimmed. But we don't really care about the DC of the junction capacitor and the low pass filter circuit. We just look at the power of the PWM. We don't look into the rectified voltage output. Okay. So for digital circuits, when we are building charge pumps, the circuit is very similar. So if you understand this circuit, this will become very simple. There's no negative voltages in digital circuits, so it's usually from 0 to VDD. And this is from 0 to VDD. That's ground. Here's the output. About 0 to VDD, oscillation. And we consider there's a VB. It's a built-in potential voltage drop, usually 0.6 to 0.7 volts from the diode. It's just built-in voltage. It's a drop. Comes with the diode. Okay. If this is 0 volts, if this is VDD, for example, let's talk about here first. VDD. What's gonna happen? You got a VDD here, right? VDD here, and cross the circuit. There's no drop, so there won't be. If you keep it on after a long time, even though you think, hey, there's VDD and it's dropping by 0.7 volts, you got a lower voltage here, but it's still not, because there's no current, so there won't be any drop across it. So there won't be any current running through the capacitor. However, once you discharge it, keep in mind, this is a very important moment over here. Once you start discharging it, so from VDD to ground, what's gonna happen? You think? It's like you have a bucket of water on the top, right? And then at the bottom, you at a moment, you start draining the water because you are pulling this down to ground. And at that moment, there will be current going through this guy and charging up the cap. Do you agree with that? That's how capacitor works.
Yeah.
Keep in mind, okay? There will be current being pulled down to the bucket or charging up the capacitor. And what's the voltage being charged up? So what's the voltage will be across the capacitor from here to here, I think? Because this will be put down to 0, right? This point is 0 volts. So what's the voltage here would be? And now there's a current going through this guy, so it's gonna causing a potential drop. So the point here will be what?
4.3.
Yeah, VG minus VB, right? Or 4.3 if it's 5 volts logic. And then because the digital signal will go up eventually. This is another thing you guys need to know. What's gonna happen? What's gonna happen if this one goes back to VDD? So the charge being stored here will stay. This is nowhere to go. This is disconnect the circuit, and this is the wall, right? So the charge will stay. So if you flip this voltage back to VDD, what are our reading here?
Wait, let's
So now this guy's VDD now, okay?
so yeah, it'd just be VDD, right?
What's the voltage here being stored over here? VDD minus VB,
Oh, that'd be.
okay? And now you add a VDD here. What's the overall voltage being observed here?
Yeah.
Okay, and usually the VB is pretty small, like 0 point something volts, and VDD is like 5 volts, right? 2 VDD will be 10 volts, and 10 volts minus 0 will give you like 9 point something volts. And if you have a one stage of charge pump, you are pumping the voltage up from 1 VDD to something very close to 2 VDD. It's just minus a little bit loss over here. That's why it's called a charge pump. Okay. Charge pump. So charge pump circuits are very important in digital circuits. A lot of times you need a charge pump to boost the voltage to a certain level in order to pass the entire signal from drain to source. So we are going to show that circuit being used for the sample hole circuit. I believe it will be on Monday. But now I'm going to add another stage to this circuit, then we'll wrap it up. So this is one stage of charge pump. Now you know how that works. If we add another stage, I think this is still just one stage. Never mind. But adding one more diode and one more capacitor. And what is this circuit? Remember?
It's a charge pump and a.
No. So this is the charge pump, right? This is a charge pump.
That's a voltage doubler, right?
Yeah, or voltage doubler. So a charge pump or voltage doubler over here. But this guy,
It's just a voltage doubler.
it's just a rectifier type of low pass filter, and we add a diode over here just to prevent the charges from going backwards. Okay, but the capacitor here will be served as a low pass filter. So you are getting, remember this is from 0 to what? Oh, is that 0? It's not even 0 actually. It's oscillating from where to where? So now remember here, it went up to 2 VDD minus VB, right? And it was VDD minus VB, because whenever this pin is being put down to 0, it's draining that source here to dump charges to the cap, right? Whenever you pull this down, at that moment, at the edge of that falling edge, this one dumps charges to this cap, and this voltage becomes exactly VDD minus VB. So eventually you are getting what? It's oscillating where to where? This is a 2 VDD minus VB, right? And this voltage here is VDD minus VB. It's oscillating between these two voltages. Does it help? Yes, because it's shooting up to a relatively higher voltage. And when you filter it out, right? So keep going like this. If you filter it out using a capacitor, it becomes this. So your DC voltage will be stabilized at the DC voltage at this level or smaller, a little bit smaller than that. At this point. Oh no, this point is oscillation, sorry. So at this point will be a DC voltage because of the capacitor, and also you are getting one more loss.
Should be 2 VDD minus 2.
This is not changing. Wait, VDD minus VB over here, and yeah, actually it's changing. So this is VDD minus, VDD minus 2 VB, and 2 VDD minus 2 VB. So that's going to be the oscillation. No, sorry. There won't be any oscillation because it's getting filtered out. So only this DC stays. It's not going back, even though potentially there will be a one more drop for the lower voltage. If the lower voltage is not getting discharged to the lower voltage, it's stabilized at the higher voltage, but you have to minus one more VB from it. Does that make sense? It doesn't. You need a quiz.
Could you redraw it?
Redraw
I'm a
it.
little lost with that.
Okay.
For the notes, you know, I do like to look back at those.
Yeah.
Having a clean version, right?
Sure.
Thank you.
Yep. So here is digital circuits, right? That makes sense because that's your Arduino's oscillation,
Mm-hmm.
0 to VDD. Okay? So whenever this pulls down, it charges this up to VDD minus VB. And whenever this goes up, it's adding a VDD to it. So this point will be oscillating from VDD minus VB to VDD minus VB. Agree with that?
Mm-hmm.
However, this guy's a filter. This guy's a filter. It won't discharge to this point, to this bottom point, right? Because this guy is, remember, so this guy is what? Is this, right? This point is this point, and this point is this point, okay? And because this is a filter, and there's one more drop, even though the bottom can potentially drop as well, but it's not reaching the bottom because it's getting filtered out by the cap. So the output over here becomes what?
VDD.
Originally it was this, right? So it becomes what? Becomes
2 VDD minus 2 VB
yeah.
minus some capacitor fluctuations.
Mm-hmm. That's the output. It won't reach the bottom because it's getting filtered out. If you choose a big capacitor, it's going to filter it out. So it's going to just fluctuating a little bit. Okay? So we will keep moving, adding more stages on Monday. And we'll start building these circuits hopefully later next week. Okay? All right. Have a good weekend.